Hi, my name is Muhammad Ashraf bin Ismanizan, and today I will be starting off the video with the introduction of our CFD project titled Analysis and Optimization Flow of the Fluid Inside Ducts. Let me introduce my teammates members, which would be Muhammad Fahim and also Luqman Hakim. So the overview of our CFD projects, we start off by talking about cements being the most important building materials in our current modern era. 26% of energy were consumed during the production of cement, but our main focus here is the duct, which plays an important role of transferring the raw materials, has a very high energy consumption, which contributes to a whopping 30 to 40% of the total cost. Hence why we need to have a suitable duct to help in reducing the energy consumption, hence cutting the overall cost. So our problem statement here is, how does the design of the duct would affect the movement of pressurized air? Hence why our hypothesis for this project is, we thought by reducing the number of vents in the duct would help in reducing the pressure drop of the air while transferring the raw materials. So there are three objectives in our CFD project. The first one would be, we wanted to prevent a significant pressure drop in the duct carrying highly pressurized air. The second one is to analyze and determine the actual airflow in the duct, and the last one would be to see how the design of the duct affects the velocity, the temperature and the pressure control inside the ANTIS simulation.
Let me explain more about how we analyze the airflow inside the duct. So this is a drawing of our ducts inside the 3D inventor. So the total length of our duct is 7.37 meter. So for your information, length of the duct is the parameter to determine the Reynolds number of airflow. So after we complete the design, we start with the geometry part in the NC software. Then we transfer the design into the geometry to start analyzing the flow inside the duct. So after open the geometry, so this is our final design of the duct for this project. So we move to the second part, which is meshing. So meshing is the process of discretizing the domain into the small volume where the equations are solved by the iterative method. So as you can see, this is our design for the meshing. So before we start meshing, we must determine the edge sizing and also the inflation of our design. So then I could identify two edge sizing for our design, which is in inlet and also at the outlet. So the inflation of our design is the wall of our design. So next, we also must to identify the inlet, outlet and wall of our design. So then this is our inlet of the duct and this is our outlet. So the wall is this is the wall of our design. Next, we go to the setup, which is the most crucial part to be done in order to make sure that our objectives are achievable. So first thing first, we go to the general. We set pressure vector for the type, absolute for the velocity formation, and steady for the time. Next, we go to the energy equation. So we set on the energy equation in order to determine the air pressure, temperature, and also velocity of airflow. So next, for the material, we set air for our case. So next, we go to the boundary condition. So there are three types of the boundary condition that I identify before at the meshing part. So this is inlet, outlet, and also wall. So for inlet, the velocity method is I set is a 7 meter per second. As the typical of the velocity air inside the duct is around 5 to 8 meter per second. So I decide to set 7 meter per second for these cases. So next, I set the initial temperature is 50 degree of Celsius. I click apply and close. And then next, we go to the outlet of our duct. So the gauge pressure of the outlet I set is a 0 Pascal. And then next, I also set the backflow total pressure is 0 degree Celsius. So next, we go to the wall. So for the wall motion, I set a shear wall, and also shear condition is no slip. So next, for the temperature of the wall, I set a 70 degree of Celsius as the temperature rise due to the two factor, which is friction loss and also air resistance inside the duct. I click apply and close. Next, we move to the solution part. So first thing first, we go to the analyzation, and then we set method as hybrid analyzation, and then we can start to analyze our data. So if we want to change the number of iteration to get more accuracy value, so we go to the run calculation, and then we change number of iteration, and then we can calculate data. So this is our graph for our case. So we move to the result to demonstrate and visualize this case. So we can identify four types of contour, which is pressure contour, temperature contour, velocity contour, and lastly is a streamline. So next is the simulation of the velocity streamline for our case.
Assalamualaikum and hi, I wish to everyone that is watching this video right now. My name is Luqman Hakim bin Syariah Azhar. I'm from Group 12. So today I will be presenting the results and also the discussions for the CFD project of our group. So without further ado, let's move on to the first slide. From figure 1, we can see that the pressure contour at the inlet part of the duct is higher compared to the outlet part of the duct. Notice how the pressure decreases from the inlet as it moves through the duct. This is because the air will lose energy due to friction against the duct side walls, as well as between the air molecules themselves, which will then translate to heat and a little bit of sound energy. The loss of energy is the cause of pressure drop inside the inlet. Next, from figure 2, when observed in detail, we can see that the velocity streamline inside the duct is lower compared to the inlet velocity and increases when it approaches the section of the duct where it bends. This is because as it approaches the duct bend, the wall of the duct must absorb the sudden impact of air in order to redirect the airflow. This in turn will increase the velocity as the air blows away from the duct wall. So now moving on to figure 3. Alright, by looking at figure 3, we are able to observe the temperature contour inside the duct. The temperature contour for the inlet part of the duct is lower than the outlet section of the duct. However, the temperature contour for the middle part of the duct is apparently higher compared to the inlet and also the outlet part of the duct. This is due to the friction between the air resistance inside the duct and also the duct walls, causing pressure and energy losses in the form of heat. So now we will be discussing the final figure, which is figure 4. For figure 4, we will be looking at the velocity vector inside the duct. The velocity vector at the inlet is overall higher compared to the velocity vector for the outlet part of the duct. We could also see that the velocity vector inside the duct wall is 0. After all the result is obtained, finally we use the Reynolds number formula, or in short known as the RE formula, to identify the type of flow that is present inside the duct. Based on the properties and boundary conditions of the duct, we obtain an RE number of 3.55 times 10 to the power of 6, which indicates that the type of flow that is present is turbulent, since the RE number exceeds 40,000. That is all from me. Thank you.
So for the conclusion, we notice how there is still some pressure drop inside the duct, in which this can be seen in the results shown. Perhaps you can fix it by increasing the duct section so it would provide an even airspeed throughout the whole system. Finally, we would like to express our gratitude towards our lecturers and team members for their contribution. Overall, I think we managed to reach our objective for this project. Thank you.